Hey guys, so I'm just going to go through some of the questions that you left here on this Google slide, and I'll post a copy of this as well because I'm going to write on it. So we only had one question for the matter unit, which was how do we calculate percent error? So if you actually use your reference tables, and when you guys sit down to take the final, it's a good idea to have the reference tables either pulled up or have your paper copy in front of you. But anytime you have to calculate something, well, most of the time anyway, the formula that you need is going to be on this last page of the reference tables, table T. So right here, the third formula down from the top, we see the percent error formula. So I'm going to go ahead and I'm going to put that down here for you. So percent error equals the measured value minus the accepted value divided by the accepted value times 100. So what that means is when they give you a question, the measured value is usually what the student got. Like usually the word student is in the question. And they tell you that the student did an experiment and they figured out that the density of copper was 8.7, something like that. So whatever the student got in their experiment, that's the measured value. The accepted, it could either be called accepted or actual value. That's what you're comparing it to. So let's go ahead and pretend that yes, my student was measuring the density of a copper bar and that student got 8.7 as a value, and we want to know what the percent error is. Now, typically, they would give you the accepted value in the question. For density, you have to be careful because if you go to reference table S, reference table S has the densities of all the elements. So element 29 is copper, and if I go all the way across to the density column, I see that the density is 8.96 for copper. So I was actually able to look that up. But anything else, guys, they would have to give you in the question. So the accepted value is what also goes on the bottom. Then you'd multiply your answer by 100 and you would get your answer. It's important that you don't type this in one big line in your calculator because your calculator will do PEMDAS and you'll come out with the incorrect answer. So here's what I'm going to suggest you do. We're going to do 8.96 minus 8.7 because we don't want any negative numbers. So you're allowed to just do the big number minus the small number on the top. Then I'm going to hit equals. Now I'm going to divide that by 8.96, hit equals, and then I'm going to times it by 100 and hit equals. So I get my percent error is 2.9%. And that's pretty good. Percent error, you want a low number. That means you're accurate. Okay. For our energy unit, this is a great question. What are the different forms of energy? So I'm just going to go over some of the really important ones. Heat or thermal energy, they're both the same thing. And we spent almost the whole unit talking about that. So the definition of heat or thermal energy is the total kinetic energy of the particles in a sample of matter. And you don't want to confuse that with temperature. Temperature is not a form of energy, and usually heat and temperature are kind of used interchangeably with each other, but they're not the same thing. Heat is the total kinetic energy of all the particles, where temperature is an average of the kinetic energy of the particles and not considered a form of energy all by itself. The units for heat are joules. Actually, the units for any energy are joules. So that could also help you remember that temperature is not energy because that's measured in Celsius or Kelvin. We also have electromagnetic or radiant energy. And really that's just light. So where you would see questions about light is when electrons, they move from the excited state back to the ground state, they emit light. So that's usually where we see talking about light energy in chemistry class. We have nuclear energy. That's energy that's stored in the nucleus. So that's the type of energy that is released when we do nuclear reactions. Like when you have a fission or a fusion reaction and we get those big explosions and big bursts of energy, it came from all the energy that was stored inside the nuclei of the reacting particles. We have chemical energy, and that's energy that's stored within bonds. So when you think about barf, if you break a bond, energy needs to be absorbed. But when you form a bond, energy is released. So energy changes in a compound when bonding changes. And those are really, oh, you know what? Let's talk about one more. Electrical energy. And that's when electrons move from one place to another. Okay, so these are the most important ones for the end of this year, I think. Okay, the atom. So we have a few questions here. I'm going to number these 1, 2, 3, just so that we can stay organized. So when is an atom's ionic radius greater than its atomic radius? Okay. So I'm gonna pick 2 elements to answer this question. I'm gonna pick sodium, and I'm gonna pick, that's a metal, it's on the left side of the table, and I'm gonna pick oxygen, that's a nonmetal. So now if you want to know the atomic radius of any elements, you can go to table S, and all the way at the end it tells you the atomic radius. So for sodium it's 160, and for oxygen it's 64. So I have 160 picometers and 64 picometers for oxygen. So what they're going to want to know is when these things become ions, how is their radius going to change? So if you want to know what kind of ion something becomes, you have to go to the periodic table and you have to look in the top right corner. So what do you see in sodium's top right corner? You see that +1? So sodium becomes a positive ion, and if I go over to oxygen, here's oxygen right here. What do you see in oxygen's top right corner? See that -2? So that's going to be important in deciding what happens to the radius. How does sodium become +1? It loses an electron. So if you're going to lose an electron, what's going to happen to your size? It's going to get smaller. So you have a smaller ionic radius if you become a positive ion. And all metals, everything on the left side of the staircase, will do this. If you're a nonmetal and you gain electrons to become a negative ion, you're gaining particles, so your ionic radius is going to get bigger. So if they give you answer choices, whoops, sorry guys. If they give you answer choices, you always want to pick something that has a negative charge. That's going to make it get bigger. Okay, question number 2, the gold foil experiment. So the Regents loves asking about the gold foil experiment because I think what Rutherford discovered was closest to what the real atom looks like now compared to like that solid sphere that we thought existed beforehand. So he noticed 2 things during the gold foil experiment. He noticed that most alpha particles went straight through the foil. That was one thing that he noticed. And the second thing that he noticed was that some were deflected. So it was almost as if they hit something inside the atom and bounced off. So these were his 2 observations. From these observations, he was able to conclude if the alpha particles are able to go right through the atom, that must have meant the atom is mostly empty space. So that was a very big conclusion. Some were deflected. So this made him realize that there is something inside of the atom because those alpha particles were hitting into something and bouncing off. So since alpha particles were positive, and he noticed that the particles were being deflected or pushed away or repelled from whatever they were hitting into, he knew that something inside the atom also had to be positive. So he said that the atoms have a positive but small, that's why not a lot of the alpha particles hit it, but very dense nucleus. So those were his two conclusions based on his two observations. Last question about the atom is what the excited state looks like. So basically, I'm going to just pick an element because I think it's easiest to do that way. Let's look at, I like magnesium. Magnesium's a good one. So in the bottom left corner of the box, you see the electron configuration in the ground state. Magnesium is 282. So let's write that down. Ground state is 282. That means that magnesium has 3 shells around its nucleus, 3 rings around it. There are 2 electrons in the first shell, 8 in the second shell, and 2 in the third shell. Whatever the periodic table says is the ground state. When an atom absorbs energy, its electrons can get excited, which basically mean that an electron jumps to the right. Okay, so now you have to be careful because this second shell, the maximum amount of electrons that can fit in it is 8. So the first answer choice that you're always going to see in multiple choice is they're going to say, okay, an electron left the first shell, leaving 1, and jumped into the second shell, making it 9. That's always going to be the first choice, but this number 9 cannot exist. So you need to make sure that you don't pick that. That electron can jump over the second shell, and it could add itself to the third shell. So that's a possibility. You could also have an electron from the second shell jumping to the third shell. So it could change to 2, 7, 3. That's another choice. Or whatever your last shell is, you can have an electron leave that shell and make a new shell. So I could have 2, 8, 1, 1. So all of those would be acceptable answers for the excited state. You just want to make sure the number of electrons don't change. So in all these scenarios, if you count up the total number of electrons, there's always going to be 12 of them. You just have 1 or more moving to the right if it's in the excited state. And you got to make sure that that second number is never higher than 8. Okay? All right, so I'm going to stop this video here and I'm going to start a new one for the next couple slides and we'll see how far we get. Okay? See you guys soon.